Okay. For the second talk of the day, we have Fiona Seibold from the Imperial College talking about these matrices for quantum-deformed superstrings. So go on.
Okay. So yes, thank you very much. And let me thank also the organizers of this virtual workshop for giving me the opportunity to give a talk. And so this will be based on a series of papers with Stein van Tongeren and Yannick Zimmermann from Berlin, and also some previous work with Ben Moore. And so maybe before going really into the heart of the subject, let me give one motivation why studying quantum-deformed superstrings is interesting. And this originates from the ADS-CFT correspondence, so the duality between strings on ADS space and conformal field theories living in one dimension less. And as you probably know, the prototypical example of this duality is the duality between the type 2b superstrings on ADS5 cross S5 and n=4 super Yang-Mills in four-dimensional Minkowski space. And an interesting property of these two theories on both sides of the duality is that in the free strings limit or planar limit on the CFT side, there is the emergence of integrability. And integrability can then be used in order to compute physical observables, such as the string spectrum or the anomalous dimension of operators. And recently, it has also, or more or less recently, it has also been applied to compute other quantities, such as structure constants and higher point correlation functions. And one motivation for why studying these quantum-deformed superstrings is to answer the following questions. So are there other superstring theories for which the integrability program can be applied? And of course, the answer of this is positive, since you can look at lower dimensional ADS-CFT setups, and this is also mainly the topic of this workshop. So you can have on the string side, you can look at ADS3 cross S3 cross D4, for instance, but there are also other string theories that you can look at. And these theories will have less supersymmetries and exhibit new features, as Ines was pointing out also in the last talk. So you can have massless modes. You can also have a mixture of Ramon and Neveu-Schwarz fluxes. However, so these examples that I've listed here are still the most supersymmetric in the respective dimensions. So you might want to go beyond that and look at less supersymmetric examples. And one way to do this is to look at integrable deformations of ADS-CFT setups. So you start with your well-known ADS-CFT setup that is integrable, and then you deform the theory in such a way as to preserve this property of integrability. So you can do, for instance, on the string side, you can do a TST transformation, so a succession of T-duality, shift, and T-duality, and this will map you string theories to string theories, and in some cases, the dual is known. For instance, you have the correspondence between the Lunan-Mullin-Madasena background, where you do a TST on the 5-sphere and beta-deformed n=4, so beta-deformed super Yang-Mills. You can also do other types of deformations, so such as TT-bar deformations or more general current deformations. And another type of deformation that you can do, and this will be the focus of this talk, this is quantum deformations, and this is when the symmetry algebra of your original theory will be deformed to a quantum group. So there are two examples, eta deformations and lambda deformations, depending on whether your parameter that enters the deformation is real or a root of unity. And in fact, TST transformations and these quantum deformations are they are special examples of so-called Yang-Baxter deformations that are an even bigger class of integrable deformations. So deformations that preserve integrability. So as I said in this talk, I will focus on quantum deformations and more precisely on eta deformations. So when the parameter that gives the deformation will be real. So the plan of the talk is the following. I will start by defining these models, these integrable eta deformations. I will then explain a bit more what this quantum group symmetry is that these models have. And then I will move to look at the quantum deformed S matrices for these models. And I will finish with some conclusions and an outlook. So let's start with defining these integrable eta deformations, and let's take a step back and look at why integrability arises in the undeformed theories. So on the string side of the duality, classical integrability will arise from the formulation of the Green-Schwarz superstring as a sigma model on a semi-symmetric space. And the idea will be to deform this semi-symmetric space sigma model. So what is this semi-symmetric space sigma model? This is a sigma model on a supercoset G mod H, where this cotic G, which is the Lie algebra of the supergroup G, has Z4 grading. So you can decompose the Lie algebra into 4 subspaces, G0, G1, G2, and G3, where G0 and G2 have even grading, and G1 and G3 have odd grading. And so this Z4 grading is compatible with the commutation relations such that G0 forms a subalgebra, and this is identified with the Lie algebra of this group H. And the action of the semi-symmetric space sigma model is the following. So you have different ingredients that appear. You have an overall constant, which is the string tension. And then you do the integral over the world sheet. So here tau and sigma are my coordinates on the 2-dimensional world sheet. Then you have gamma ij, the Weyl invariant metric on the world sheet, epsilon ij, the antisymmetric tensor. And then you take the supertrace of 2 left invariant Maurer-Cartan forms, D inverse dg, and you insert the projector in the middle. So here this G is a supergroup valued field that takes values in this supergroup G that I introduced previously. So what are the properties of this action? So there is a global left acting G symmetry, and this comes from the fact that you constructed the action using the left invariant Maurer-Cartan forms, G inverse dg. Then you also have a local right acting H symmetry, and this is why you need, so in order to ensure that, you need to insert this projector here. You also have invariance on the world sheet diffeomorphism and also fermionic kappa symmetry that will, so this is a symmetry such that the fermionic degrees of freedom is the same as the bosonic degrees of freedom. And then finally, you also have classical integrability in the sense that the equations of motion of this model, you can recast it into the flatness condition for a lax connection. And so here, if you choose different quotients, you will generate different different models. So for instance, in the case of ADS5 cross S5, the quotient that you need to consider is PSU 2,2/4 divided by the isotropy group of the 5 sphere and the ADS5. And then you also have different quotients for the different models. So for instance, you also have ADS3 cross S3 cross D4 and so on. And so here, now we want to deform this model in a way to preserve integrability. And in order to define the deformed model, there will be 2 new ingredients with respect to the undeformed model. So one is a real parameter eta that takes values between 0 and 1, and this is the deformation parameter. So when eta is equal to 0, you will recover the undeformed theory. And then the second ingredient is a Drimfeld-Jimbo operator, so a linear map from the Lie algebra to itself, and it acts as follows. So if you take this symmetry algebra, you decompose it into Cartan elements, positive and negative roots, then this Drimfeld-Jimbo operator will annihilate the Cartan elements and multiply with plus or minus I the positive and negative roots. This operator, since we want to preserve integrability, will have to satisfy some constraints. And one is that it is antisymmetric with respect to the supertrace, and the other is that it satisfies the so-called inhomogeneous classical Yang-Baxter equation, that is an equation of this form. So now that I have defined the two ingredients that will appear in the deformed model, I can show you the action of the deformed model. And you see that it's just the insertion of this non-trivial operator between the two left invariant Maroccaton forms, and you also slightly modify this projector. So, and indeed, here, so when eta goes to 0, we recover the undeformed semi-symmetric space sigma model. So what are the properties of this deformed model? So first of all, because of the insertion of this non-trivial operator, the global left-acting G symmetry will actually be broken to just the Cartan element. So you will have a set of U1s. The local right-acting H symmetry is still there. And you also have Velchy diffeomorphism, fermionic kappa symmetry, that's also still there. And again, because of your clever choice of operator R, this Trimfel-Jimbo operator, you will preserve in the classical integrability, meaning that again, you can write the equations of motion as a flatness condition on a lax connection. Furthermore, and this is something I will come back to later, this theory actually has a hidden symmetry, and this is a quantum group symmetry, GQ. So I will define this later. And this parameter Q is related to the deformation parameter eta and the tension of the string. So here Q is real. And so this one can then wonder whether the model defined in such a way is unique. And this boils down to understand whether the Trimfel-Jimbo operator that we have used to construct the model, whether it's unique or whether we can choose different types of Trimfel-Jimbo operators. And this will actually depend on the symmetry algebra. So if G is a complex semi-simple D algebra, or when you take a compact real form, so for instance, SU4, then you actually have a unique Trimfel-Jimbo operator, and this will define for you a unique eta deformation. If G is non-compact, is a non-compact real semi-simple algebra, so for instance, SU2, 2, and this will be important in the context of strings on ADS spaces. You can have different Trimfel-Jimbo operators, but the deformations that you generate using these different Trimfel-Jimbo operators, they will be related by a complex field redefinition. And the case that will be of interest to us in this talk is when G is a semi-simple superalgebra as opposed to an ordinary D algebra. So for instance, SL2/2. And in this case, you can actually have different types of Trimfel-Jimbo operators that are associated to different thinking diagrams of the superalgebra. So superalgebras have different thinking diagrams, and depending on which one you choose to construct your Trimfel-Jimbo operator, you will actually generate different types of eta deformations.
Sorry, may I ask a question?
Sure.
Do you understand that the number of operators is equal to number of non-equivalent choices of Borel subalgebra?
Yes.
Okay.
Yes. Okay, and then so here I mentioned that you can have different eta deformations, and well, one way to characterize these different eta deformation is to look at the background they generate. So you choose a specific parametrization for this supergroup valued field. You expand to quadratic order in the fermions, and you compare the result to the standard Green-Schwarz string, and this will allow you to obtain the metric, the B field, and the Ramon-Ramon fluxes. And a priori, these quantities will depend on the Trimfel-Jimbo operator you choose, and this is why I have this upper script R, and it will also depend on the deformation parameter eta. And what you find is that for these different models, you will actually, so if you take different thinking diagrams for the Trimfel-Jimbo operator, then you actually generate the same metric and B field. So again, up to complex field redefinitions, because so in the case of ADS, and you will have different Ramond fluxes. So let's look at the more concrete examples. So let's look at ADS 5 cross S5. In this case, the symmetry algebra of the undeformed theory is PSU 2,2/4, and this is a rank 7 superalgebra with many different Dinkin diagrams. So here I will focus on two of them. One is the so-called distinguished Dinkin diagram. So it's distinguished because it has the maximum number of bosonic simple roots. So here the bosonic simple roots are denoted by a circle, an empty circle. And there is one unique fermionic simple root that is represented with the circle with a cross. And in this case, the metric and B field is supported by one form Ramond flux, 3 form, and 5 form. And interestingly, it does not solve the supergravity equations of motion. Another type of Dinkin diagram that you can consider is the fully fermionic Dinkin diagram, so where all the simple roots are fermionic. And in this case, the background is given by, so the metric and B field is supported by a Ramond 3 form flux and 5 form flux. And in this case, it actually satisfies the supergravity equations of motion. And in fact, it's only when you consider this type of Dinkin diagram, so only this fully fermionic Dinkin diagram, that you will generate a deformation whose background solves the supergravity equations of motion. Another example is the case of ADS 3 cross S3 cross D4, so pure Ramond case. In this case, the symmetry algebra is given by 2 copies of PSU 1,1/2. And since you have these 2 copies, you can actually define a 2-parameter deformation where you deform the 2 copies in different ways. And again, you can look at what happens when you consider different types of Drinfeld-Jimbo operators. So for instance, if you take, again, the distinguished Dinkin diagram of PSU 1,1/2, then you find that you have a 1-form flux, a 3-form flux, and a 5-form flux. And here you have, these will depend on 2 parameters, eta left and eta right, that are the deformations, so the intensity of the deformation in the 2 copies, in the left and right copy. And again, you find that it is not a solution to the supergravity equations of motion. The same happens when you take the so-called mixed Dinkin diagram for PSU 1,1/2, where you have 2 fermionic simple roots and 1 bosonic simple root. And again, it is not a solution to the supergravity equations of motion. And similarly to what happened for ADS 5 cross S5, it's only when you consider the fully fermionic Dinkin diagram that you obtain a background that solves the supergravity equations of motion. So these eta deformations, depending on which Dinkin diagram you choose to construct them, you see that the backgrounds that you generate will be different, and actually some of them will be solutions to the supergravity equations of motion, and some of them won't. So they are quite different. And so something that I find like a funny observation, but I won't go into more details, is that these two theories that are not supergravity equations of motion, they're actually related by a TST in the torus direction, and this TST depends on the deformation parameters. So now I've mentioned to you before that these theories actually have a hidden quantum group symmetry, and this will be very important for the rest of the talk when I will focus on the S matrices of these theories. So let me give a bit more details on what this quantum group symmetry is. So again, let me take the Lie superalgebra and decompose it into Cartan elements, positive and negative roots. So I will take the same decomposition as the one I chose in order to construct the Drinfeld-Jimbo operator. And so the commutation relations are dictated by the Cartan matrix, and they take the following form. And it's possible to promote this algebra to a Hopf algebra by introducing an additional operator. So this delta, this coproduct, which is a Lie algebra homomorphism. And now we want to understand how this, what the Drinfeld type for quantum group is, so how to deform this Hopf algebra. And the way you do this is that you change the commutation relation between positive and negative roots. So instead of having just h that appears on the right-hand side, you will have now some factors q to the h. And you also need to deform the coproduct of the simple roots, again with some factors q to the h. And when you take q, the limit q goes to 1, then you recover the original Hopf algebra. And let me stress that, so in order to, so this Drinfeld type, this Drinfeld quantum group, again, you see that it will depend on the choice of the compositions of Cartan Weyl basis that you choose for the symmetry algebra. And these different eta deformations will have a Q-deformed symmetry where you take the same Cartan Weyl basis as the one that you chose to define the Drinfeld-Jimbo operator. And now let's see how these different, so what happens when you take different thinking diagrams. So we take so different Cartan Weyl bases associated to two different thinking diagrams. And in this case, you obtain that the Q-deformed algebras are isomorphic. So you can find this Lie algebra homomorphism omega. And you also find that the Q-deformed coproducts, they are related by a twist. So by this operator F that satisfies the Drinfeld twist condition with the coproduct. So in the case of SL2/2, you can have two different thinking diagrams. So you have this distinguished thinking diagram and this fully fermionic thinking diagram. And these are actually related by a so-called generalized Weyl reflection in this second simple root. So this generalized Weyl reflection, what it will do is that it will change the nature of the two roots adjacent to the root on which you do this reflection. And in this case, the twist that relates to two coproducts is precisely involves this simple root that you use on which you do the Weyl reflection. So the twist takes the following form, and this is true in general. So this twist will always be given by the exponential of a positive tensor negative root. So this is the root on which you do this generalized Weyl reflection that allows you to go from one thinking diagram to the other. Good, so now that we have a better understanding of this quantum group symmetry, I want to look at the exact S matrices for these theories, but perhaps there are some questions before that. If not,
I forgot, I'm sorry, I have a question. So these quantum groups, do they have a center?
I mean, I think it depends whether your original symmetry algebra that you started with has a center or not.
So in the case of quantum group, quantum determinant is not the center?
The quantum determinant. So I don't know exactly what the quantum determinant is.
We can talk later about this.
Okay. Okay, so let's now look at the quantum deformed. So the S matrices, the worldsheet S matrices for these eta deformed theories, and the path you follow in order to find the worldsheet S matrices is the following. So you start from the deformed sigma model. So this is the model I showed you in the first part of the talk. So then you need to get rid of the redundancy in the description. So due to the, for instance, worldsheet diffeomorphism. So you need to fix light cone gauge, and also you need to choose a kappa symmetry gauge. This will allow you to define the gauged fixed model. And there the model will be defined on a cylinder of fixed radius. And then you go to the compactification limit. So you take this radius going to infinity, and the theory you end up with is a massive two-dimensional quantum field theory. And you can study the worldsheet excitations, so the excitations, and this will give you the scattering matrix. And in order to construct this S matrix, I will make two assumptions. So one is that the Q-deformed symmetry algebra, it will extend to the quantum theory. And the second assumption is that classical integrability also extends to the quantum theory. So you will have quantum integrability. And this will actually impose strong constraints on the S matrix. So you will have no particle production. So the number of incoming particle will be the same as the number of outgoing particle. You also have that the momenta are just transmitted. So the set of incoming momenta is the same as the set of outgoing momenta. There is just a reshuffling. And finally, you have the property of factorization, meaning that the n-body scattering event, you can factorize it into a sequence of two-body scattering. So these, the crucial ingredients in these theories, for these integrable theories, are the two-body S matrix, from which you can then construct the n-body S matrix using this factorization property. And so there will be also a constraint on this two-body S matrix, and this you can see by looking at the scattering of three different particles. So you can do the scattering in different ways, in two different ways, depending on which particles scatter first, so 1 and 2 or 2 and 3, and requiring that the result of this event gives the same results for the two perspectives. This will impose the following constraint on the S matrix, and this is the quantum Yang-Baxter equation. So S12 times S13 times S23 should be equal to S23 S13 times S12. And furthermore, the two-body S matrix can be bootstrapped, at least partially, using the symmetry of the quantum theory. So in our case, this will be the Q-deformed symmetry. So let's look at the example of ADS5 cross S5. So here we need to look at the symmetries of the light cone gauge fixed theory. So we started with in the sigma model we had the symmetry algebra PSU 2,2/4, and when we light cone gauge fix, there will be a symmetry breaking, and we will end up with two copies of SU2/2, and here we will have also a central extension that appears. Now, in the case of the Q-deformed model, what will happen is that we will start from the Q-deformed PSU 2,2/4, and the symmetry breaking pattern is of this form. So you will end up with two copies of SU2/2. One is deformed with Q, and one is deformed with 1 over Q. And so let's see what happens if we consider different models. So if we take models associated to different thinking diagrams. So for the distinguished thinking diagram, the symmetry breaking pattern is the following. So you end up with these two SU2/2 that are also associated to the distinguished thinking diagram of SU2/2. And in the case of the fermionic PSU2,2/4, you end up with fermionic SU2/2 Q-deformed. And as I mentioned previously, these two, so one thing is that since we have these two copies, it will be sufficient to construct the SU2/2 centrally extended and Q-deformed S matrices. So we just look at one copy. And the second observation is that these two, we have seen that the coproduct for these two different Q-deformed algebras, they are related by a twist. And we therefore also expect the S matrices to be related by a twist. And the twist is of the same form as the one that I showed you previously, but here you also have the braiding that appears, and this is because you consider the central extension. So let's see, let's look in more details at these Q-deformed SU2/2 centrally extended S matrices. So first, for the distinguished Dinkin diagram. So this S matrix has actually been constructed already in 2008. And it has several properties that you might want of an S matrix, namely it satisfies braiding and matrix unitarity. It solves the quantum Yang-Baxter equation. So this consistency requirement for the S matrix, for the integrable S matrices. And you can also impose crossing symmetry. And furthermore, there is a bosonic Q-deformed SU2 plus Q-deformed SU2 suborf algebra. So you can identify in your S matrices two 4x4 blocks that have that are of the form of the S matrix of the SU2Q S matrices that takes this form.
Excuse me, can I ask a question?
Sure.
So I haven't worked on superalgebras for many years, but last time I tried to build S matrices in the context of superalgebras, I remember big problems with unitarity. Usually supergroup symmetry precludes unitarity because there are always states with negative norm square. Now you seem to be not worrying about this and claim that your S matrix is unitary. So can you comment on this? I mean, is it obvious, for instance, is the field theory unitary? Is the Hamiltonian Hermitian? I mean, again, usually when you have supergroup symmetry, this is not possible.
I mean, I might be mistaken, but I thought that these S matrices that appear in a ADS-CFT setup, so for instance, the SU2/2 S matrix of for ADS 5 plus S5, they are unitary, that they have this braiding and matrix matrix unitarity property.
I'm happy to believe that, but I'm a little bit confused as where this comes from. It's just my ignorance. Probably somebody can explain this to me, but didn't we start with a theory that had SU2/2 symmetry? I mean, the Lagrangian had that symmetry.
Yes,
am I correct?
But I mean, these properties that I list here are also valid in the undeformed theory. So yes. Perhaps it's easier to just look at the undeformed theories, and there, I think. I mean,
okay, it's probably something I should learn, but I would have been happy if somebody explained how superalgebra symmetry can be made compatible with unitarity. But
I mean, maybe there is a subtlety on how this unitarity condition is defined.
Yes, there might be something like this. Will you explain more, for instance? Will you be able to do the bootstrap and tell us about the maybe bound states and stuff?
No, so I cannot explain more about this. I'm sorry.
How about TBA?
So no.
Sorry. Go ahead. Please go ahead.
If I can make a comment, I don't know if that helps at all, but in the ordinary undeformed case, which is a little simpler, one starts from a unitary finite dimensional representation of this SU2 /2 superalgebra, which exists, and doing the ordinary bootstrap on that is possible to fix an S matrix which has unitarity in the, well, which is basically it turns out to be very closely related to the Hubbard model S matrix, as it turns out. And,
including, and you're having also anti-particles, right?
Yes, there is a notion of anti-particle. There is a notion of crossing symmetry. It's a little bit different. It's not a relativistic theory. That might be one of the catches.
This is probably what I'm missing. Okay, I see.
Yeah.
But
well,
in Hubbard model, Hamiltonian is Hermitian, and what Hubert referring that he wrote a paper about Q deformation with magnetic field where Hamiltonian is not Hermitian. It doesn't even commute with its own Hermitian conjugated. So that's my guess what's Hubert referring to. So maybe we can discuss this later.
Yeah, sure.
Well, Hubert, just to comment, antiparticle is not in the field multiplet. It's some other multiplet. So it's not unitary in this sense. It's generalized motion unitarity. So you're not missing that.
Yeah, I think this explains it all. Okay.
Yeah, it's like contravariant versus covariant. They're different groups of representations. They're not.
Yeah, and you're not mixing them.
You are not mixing them, no.
You're not mixing them. You're having only one kind. Is this physically meaningful?
Well, in this model, yes.
It is. Okay, good. I'll take your word for it. Okay.
Okay, thank you for the discussion. All right, so it's possible to construct this S matrix using the symmetries, and then in order to be sure that you are doing the right thing, you should also compare it to the to the perturbative, so the S matrix, the well-sheet S matrix that you obtain using perturbative calculations, and you actually obtain a matching with the tree-level. So the tree-level expansion of the exact S matrix matches the perturbative calculations, the tree-level calculation. If you use a starting model, this eta deformation that is based on the distinguished thinking diagram, and you identify the deformation parameter Q in the way that I have already mentioned previously. And then you can also look at what happens when you consider the fermionic thinking diagram. And again, you find an S matrix that satisfies braiding and matrix unitarity. It solves again the quantum Yang-Baxter equation, so you have compatibility with integrability, and the crossing equations are the same. In this case, however, the SU2Q plus SU2Q is no longer a sub-Hopf algebra, so these two blocks that I have highlighted before will be deformed in a way. So we will lose this SU2Q sub-Hopf algebra. In this case, again, you can compare the expansion of this exact S matrix with the tree-level calculation, the perturbative calculation, and you find, again, a matching if you use a starting point, the eta deformation that is based on the Drinfeld-Jimbo operator constructed using the fully fermionic thinking diagram, as expected. And so it seems like these two S matrices are quite different and not related by one particle change of basis. However, they are, as expected, related by a twist. So this twist that I have showed previously, and in this case, just to show you how this twist looks. So you have it will act as the identity, plus for some terms you will have these contributions where you have the braiding that appears and also the representation parameters. And you see that this twist is so it's not factorizable, and this is why the two S matrices are not, or do not seem to be related by a one particle change of basis. And you can also look at areas 3 cross S3 cross T4. In this case, the symmetry breaking pattern so it's the following. So you have your two copies, PSU 1,1/2 left plus PSU 1,1/2 right, and you end up with 4 copies of SU 1/1. And the same in the Q-deformed case. So here you can have two different deformations into two copies, Q left and Q right, and you end up with, again, SU Q left 1/1 plus SU Q right 1/1, and you have two copies of that, and you have the central extension. So let's look at the three theories that I have mentioned at the beginning of the talk when you use different Deacon diagrams for PSU1, 1/2. And in this case, so this SU1/1 actually has only one type of Deacon diagram, so you can only have this fermionic simple root, and therefore all these theories will actually share the same exact S matrix. And this has been constructed when you have two deformation parameters, and the three-level expansion again matches with calculations from perturbation theory. So all these different eta deformations, they have the same S matrix. So let me now come to the conclusions of this talk. So what have we seen? So first, we have seen that a way to generate new integrable theories is to look at integrable deformations. So when you deform the theory that you know is integrable in such a way as to preserve this property. And in this talk, I focused on eta deformations that correspond to a Q deformation. So they promote the symmetry algebra to a Drinfeld type quantum group. Another point that we have seen is that eta deformations of superstrings, or equivalently Q deformations of superalgebras, they are not unique. And in fact, there is only one type of eta deformations, or rather one class of eta deformations that are supergravity solutions. And this is when you consider your Drinfeld-Jimbo operator associated to the fully fermionic Deacon diagram. And we have also seen that the exact Q-deformed S matrices, they are related by a twist. And there is a matching between the expansion of the exact Q-deformed S matrices and the perturbative calculations. And finally, these S matrices satisfy the quantum Yang-Baxter equation. So there is a compatibility with integrability. So there are, of course, open questions. And one is how does the physical, the twist affect the physical observables? So for instance, the spectrum of the theory, and this is actually, so the beta equations for the distinguished S matrix have been obtained in this paper in 2008, and I have some ongoing work with Alessandro Sfondrini about finding the beta equations for the fermionic case. And then another open problem is the interpretation of the twist at the level of the background. So how we can go from one background to the other. And of course, an interesting point to address would be to understand better the Weil anomaly in these eta deformations. So whether it's possible to make sense of these theories that do not solve the supergravity equations of motion, whether it's still possible to make sense of them in the context of string theory. Another open problem is the connection between these eta deformations and lambda deformations. So this so-called Poisson-Lie duality, and it would be interesting to see how this extends to the super case when you consider superalgebras. And finally, a broader open question is the interpretation of these Q deformations in the context of holography. So since in this talk, I focused on the ADS part, so I deformed the ADS part of the, I deformed some ADS strings that are imported in the context of ADS CFT. So one might wonder how the jewels are deformed and whether there exists some deformed ADS CFT correspondence. So thank you for your attention, and I welcome questions.
Great, thanks, Fiona. Are there any questions? Yeah, Alessandro,
Yeah, I can ask a question. Is there a way to understand why only the all-fermionic thinking diagram gives a background which solves the supergravity equations of motion? It seems very, very interesting.
No, I mean, I don't have a good answer why this is the case, but you can. So if I remember correctly, in the case of non-abelian T-duality, you can also have some anomaly that appears there if you have a non-unimodular algebra. So, and a similar thing happens here. So in order to be a supergravity solution, these R matrices have to satisfy a so-called unimodularity condition, and it's only in the case of the fully fermionic thinking diagram that this is satisfied. But I don't have a good answer to the question why this is the case.
Okay, I see. Yeah, makes sense.
Any other question?
Oh, it's related to the diagrams. So first a comment, can you show picture where Dynkin diagrams with PC224 were drawn?
2 to 4, I mean, there are these two.
For instance, it's okay. So, so you consider actually non-compact real form here. So
yes.
It's actually useful to denote the fact that it's a non-compact. So you can draw any mark you want, like double circle. For the node, he's actually SU1, but not SU2.
I agree, but so what will happen is that when you take, so if you stay within the class of one Dynkin diagram, but different real forms, then the backgrounds that you generate will be related by analytic continuations.
Okay, so basically you're saying that no, but there is only one way to draw Dynkin diagram which is compatible with highest weight story. So if you try to generate different, I mean, if you choose, you see, when you have non-compactness, one direction is going down up to infinity, and the other is you have clear upper bound. It's so you cannot choose different Borel subalgebras to be compatible with highest weight representation theory. It's like only one choice which is good. So I don't know when you say you have different options, they are related. I'm not sure. I know only one option really, and this. I mean,
okay, then so all I want to say is that you can, yeah. So what's yeah, but even okay. So all I want to say is that even when you have only one, so if you choose one type of thinking diagram, then you can still have different types of Dirichlet-Jimbo operators, but the eta deformations that you construct out of them will be, I think, related by complex field redefinition. I'm not so yeah. Probably you stay within the same real form, but you can still define different models there.
Well, okay. So I mean, just if you denote it on the diagram, it's more believable that you did the correct deformation, because for the moment I say maybe you did compact deformation instead of non-compact one. As I say, I do not know. And the same actually for all crosses. I mean, if it's non-compact forms, there are two different types of crosses to Uber, covariant and contravariant crosses. And I mean, half of them are contravariant actually. They're not equal. So, but in the case of fermions, it's easy to make particle whole because it's one step away. So maybe it's not crucial. So, is it? I mean, did you consider this point? I mean, so well, like half of fermion should be filled to make correct vacuum for non-compactness.
Yeah, I don't know exactly. Yeah. I mean, all what I do is that I change this operator R in the definition of the action I'm not sure. And then I can say, I can say it is related to this choice of thinking diagram. But yeah, I was a bit sloppy in the sense that I always here when I say the thinking diagram, I consider the complexified superalgebra. So I was not very careful with the SU2/2 and so on.
Okay, but now the question, I mean, you know, there are two other popular thinking diagrams on the market, with 2 crosses and with 4 crosses.
So, sorry?
There are 2 other popular thinking diagrams, with 2 crosses, which is good for classification of conformal primaries, and with 4 crosses, which is again CFT favorite. So okay, why didn't you try them?
Yeah, so one comment is that obtaining the different backgrounds is actually quite hard. So what one could do it for these 2 different cases that you mentioned, but it will be complicated. And second is, all what I can say is that about these 2 backgrounds is that they won't solve the supergravity equations of motion. So here I just wanted to show you 2 different cases where one background will be a supergravity solution and the other is not. And so you can, of course, also look at different thinking diagrams as you suggest, but then obtaining the background will be difficult. And second, it might not be that interesting because you're sure that the background will not be supergravity solution because this operator will actually not solve the unimodularity condition that I mentioned.
Okay, thank you.
Any other question? I'm going to ask a question about so I'm going to go a little bit out and ask about the 3-parameter deformation of ADS3 equals 3 equals to 4.
Yes.
And I imagine with what you said to Alessandro, it's already answered, but I guess that in that case, also the fully fermionic thinking diagram is the one that is going to give you a supergravity background, isn't it?
So I cannot confirm that in the sense that the condition of unimodularity was shown to be sufficient to have a supergravity solution in the case of 1 or 2 parameters, but not 3. So it's, I mean, it looks like it will be this way, but there is no proof of this statement.
Okay. Then I think we can thank Fiona again for her talk. And I think we can